Okay, I really am going to finish the radiometric dating today. I was looking at the calendar and I saw that at 1 p.m. today I have an appointment to go see Caitlin present her research, Caitlin Toy. It's going to be in room 130, right across the hall here. So you can come and support your classmate, because I plan on doing that, supporting. All right, let's get started. What is this picture? The Shroud of Turin. And some people believe that's the face of Jesus. They believe that this was the cloth that he was wrapped in when he was put in the grave. How would you know if this is actually the piece of cloth that Jesus was buried in?
Carbon dating.
Now, carbon dating, we are scientists after all, aren't we, everyone? Carbon dating isn't going to tell you that it was, but it can tell you that it wasn't. Right? Carbon dating could say, hey, this is from the same time as Christ. Or it could say, this was not from the same time as Christ. Now, I have a slide with more information on it later, so I will fill in the details there. But this is something we're definitely going to finally get to in today's lecture, is dating, and we'll talk a little bit about the Shroud of Turin and what carbon dating has told us about that shroud. That's my teaser to make sure everybody's interested in today's lecture. Okay, but first we're going to start with 2 clicker questions on what we studied in class on Wednesday, because that was the last class period we had. Why must neutrons be, quote, thermal, end quote, to produce a nuclear fission chain reaction? Yes, do you remember to turn in your reports from the Nebraska Academy of Sciences meeting? If you don't have it with you now and you haven't already turned it in, just turn it in real soon, okay? I'm not going to say no soup for you if you don't have it turned in. Still waiting for you, Isaac. There we go. Okay, so we did not have a strong consensus here. But rather than having you discuss it, I'm going to ask, turn it this way so I don't know who I'm asking. Come on. I'm going to ask this person here. Hannah. Let's start with something simple, Hannah.
Okay.
What does it mean if the neutron is thermal? No. It's an important term, though. That's why I started with it. Thermal, in terms of neutrons, means something different than you would tend to think. Thermal means that it has a kinetic energy that is low enough that it would be assigned a reasonable temperature, a few thousand kelvins, that it's in thermal equilibrium with its environment. Non-thermal means that its temperature is higher than the temperature of its environment. And so thermal means slow. I don't have the graph here that we had the last 2 class periods that showed the absorption of the uranium-238, uranium-235, and plutonium-239 of neutrons. But plutonium-239 and uranium-235 can only absorb slow neutrons with any reasonable efficiency. Uranium-238 doesn't absorb neutrons with any efficiency, really. The only neutrons that 238 will absorb are superfast neutrons. So superfast neutrons can then be collided into uranium-238 to go through a sequence to make neptunium and plutonium. But for fission reactions, we have to have one of those 2 isotopes, and we have to have slow neutrons that are in thermal equilibrium with their surroundings. Next question. No, not next question. I wonder if I deleted the next question. I thought it was right next. Well, we'll just move on, and when the question comes, we'll answer it. Beta decays. There are two types of beta decays. Up to this point, I have concentrated mostly on the beta decay, which is a beta minus an electron coming off. Now, there's a little interesting history with beta decays. Beta decays, when they were first observed, people looked at the mass and they looked at the energy of the electron and they said, ruh-roh, we don't have conservation of energy. Now, what would the mass have to do with this?
It can be converted into energy.
Okay, mass can be converted into energy. So when we have the decay, the total energy you start with, let's say you start with a still parent, it's just going to have its rest energy of mass of the parent. So energy initial is mass of the parent times the speed of light squared. And then when it decays, you're going to have the energy final is equal to the mass of the daughter plus the mass of the electron. I'm going to take, this is the daughter nuclide. Oops, that's not the electron. The daughter nuclide, and that's the electron. So the mass of those two combined times c squared plus the kinetic energy. Now that kinetic energy, because of the grand disparity of masses, it's almost exclusively in the electron. But that should be the energy final, and for conservation of energy, these two energies should equal each other. And what they found was that the energy final was a little bit less. And so if you're a physicist and you find that the energy is a little bit less, what do you do? Yeah, you go back and you change your hypothesis. You have either conservation of energy was wrong. Now, Einstein showed that conservation of mass was wrong, so that's already accepted that something had been believed was now incorrect. But either conservation of energy is incorrect, or there's something else. And it was only a small deviation. I know most of you, when you're doing your homework, if you find that you're different in the third decimal place, you're like, probably round off error, right? I mean, that's pretty human. I'm not disparaging you with that. But when you're doing very careful measurements, you don't just shrug your shoulders. And so they went back and they said, well, either we're all wrong about conservation of energy, and conservation of momentum for that matter, or there must be some particle that we haven't found that's also being created in this decay. And so they said, well, if this particle had a charge, we would have found it, because it's really easy to find charged particles, right? They interact strongly with other charged particles. So it must not be a charged particle. And it must not be a big one, because it's a big one, we can find those easily too. So it must be a tiny neutral particle, and so they introduced the word neutrino. It's a neutral tiny particle. And then they went searching for it, and they've isolated the neutrinos. We have 3 flavors of neutrinos: the electron neutrino, the mu neutrino, and the tau neutrino. So that's why it has a subscript of E, because it's the electron neutrino. That's not a V, that's the Greek letter nu. Now there's one more thing about the notation. Notice there's a bar above the nu. That bar means it's an antiparticle. So what's particles, antiparticles? I don't know if any of you, read anything about Washington State University, go Cougs, recent discovery of the, quote, what do they call it, negative mass material, where they create a Bose-Einstein condensate of rubidium atoms. They took rubidium atoms, they slowed them way down so that they could get them to behave like bosons and bond together. One of the things that the article I read about that talked about the Dirac sea. And the Dirac sea is really the beginning of the understanding of what an antiparticle is. So here's what Dirac noticed. Here's energy equals 0. Here's energy equals mass of electron times c squared. And he said, we have electrons that occur with energies starting at mass of electron c squared and going up. So we have lots of electrons here. And then he said, what if these electrons were actually created from a region down here that was initially completely filled. Now I made the top one look like it, has lots in there. But you start with this region that's initially completely filled. And then you take an electron down here and you have light hit it. So you have a photon that comes down and hits here. And you have the whole photoelectric effect thing happen on these electrons that were bound down here. And so you have the light is absorbed, and the electron goes from being down here with a negative energy to having a positive energy. But if that happens, it's going to leave behind a little spot here, a little energy state that's missing an electron. It's a hole in the Dirac sea. He calls this region down there that's completely filled with electrons the Dirac sea. And so then we have a pair. I'm going to erase all of this stuff here and just put this one electron now. I have my electron up here with its hole, the place it left in the Dirac sea. So this thing down at the bottom is called the Dirac sea. Oh boy. And Dirac posited that the universe is just filled with electrons. We have electrons filling every place in this Dirac sea, but they have these negative energies, and we don't interact with them. But if light of the right energy hits there, it will it will move the electron from the bound energy state to an unbound energy state, where it's a free electron. So things up there in the top are free electrons. And down here we have a hole, which is also called an anti-electron. So the anti-electron is a place where there's a missing electron. And so he posited that that's how pair production occurs. You can have a photon that is absorbed and produces an electron and a positron. It's anti-electron. Another name for anti-electron is positron. And these are two particles that if they meet, they annihilate. Now with this picture, with the Dirac sea picture, if the electron meets the hole, it will just follow in energy to fill that hole and give off the energy difference in the form of a photon. And so this idea gave us the idea of antimatter, and I think that's the origination of the idea of antimatter. It's not what is typically believed is the case. They actually typically believe that there really are particles that are positrons or anti-electrons. But based on this, we now have a theory that every particle has its antiparticle. Particle that's just like it, except for the charge is opposite. There's a couple other quantum properties that are opposite. And if the two meet, they annihilate. Convert all of their energy, all of their mass into a photon. And so that's what antimatter means. We have particle matter, particle antimatter. The two are exactly the same except for a few quantum numbers that are flipped. And if they meet, they will annihilate and create a photon. So this here, the antineutrino, it's the mirror image of the neutrino. Why all this thing about matter, antimatter? We're not going to have time to get into particle physics, but in particle physics, we have lots of conservation laws. So far we've learned conservation of energy, we've learned conservation of charge, we might have learned conservation of baryon number, that is the number of protons plus neutrons is constant. Well, in quantum physics, or in particle physics, we'll have conservation of all kinds of things. Conservation of lepton numbers. We have 3 types of leptons. Leptons are particles that are very light. And the 3 types are the electron, the muon, and the tauon. Those are fundamental particles. You can't break them into smaller things. And the muon, how many people have heard of a muon? Okay, a few people. The muon, you can think of perfectly accurately as a heavy electron. Muons have all the properties electrons have, except for more mass. And the electron has its neutrino, the electron neutrino. The muon has its neutrino, the mu neutrino. And then we have the tau particle. The tau particle is like an even heavier electron. Lepton means light particles because electrons are light. The tau particle, which is a lepton, is more massive than a proton. So it doesn't really fit that light particle anymore. But the tau is like a super heavy electron. And then you have the tau neutrino. So we have 3 types of neutrinos. That's why we have to have that. And for every particle, there's an antiparticle. So for the electron, there's an anti-electron. For the proton, yes, there's an antiproton. For the muon, anti-muon. For the neutrino, the anti-neutrino. And we have conservation of the electron-lepton number. That is the number, the quantum number that's associated with both electrons and electron neutrinos. And so in this case where you had how many electrons in the nucleus initially? What's the nucleus made out of? Protons and neutrons. How many electrons? 0. So we start with no electrons. We can't have a change in that lepton number. We can't have a change in the number of electron leptons. And so if you create an electron, there wasn't one before, so your electron-lepton number went up by 1. Well, you have to have that come down by 1 as well to keep it at 0. And so that's why it's an anti-electron neutrino, because the antiparticles carry a negative for the lepton numbers. And so you have conservation of electron-lepton number that goes along with that being an anti-electron neutrino. All of that said, that's a beta minus decay. Where did the electron come from if it wasn't in the nucleus? It was created. There was no electron. You had an interaction between the quarks that make up the protons and neutrons that created the electron and the electron antineutrino. And so energy was converted into making those. So they didn't come from somewhere, they were created. They came from energy. Now we have the beta plus decay. That was beta minus, beta plus. It's got a positive charge. That's not an electron anymore, that's the anti-electron, more commonly known as the positron. And notice there's no bar over the electron neutrino now. That's a regular electron neutrino because the positron carries a -1 electron-lepton number. You need the neutrino to have +1. So once again, you have the electron-lepton number start at 0 and ends at 0. Where did that positron come from? It was created, right. It wasn't there to begin with. It was created. So this is the beta plus decay. Why are they both called beta? Because positrons and electrons behave exactly the same, except for one's a positive charge and one's a negative charge. So the decay particle is going to look exactly the same, except you put them in a magnetic field, one bends that way and one bends that way. You put the neutrino in a magnetic field, what's it going to do? Nothing, because it's neutral. Has to have a charge to interact with the magnetic field. Okay, the radiometric dating. I told you, we're going to get there. Radiometric dating is based on the time it takes for something to decay. We had a lab where we looked at the decay rate. We were looking at the number of decays per second. We call this the activity. The activity is the number of decays per second. We could have just as easily done our calculations, not our measurements, but our calculations using the number of radioactive nuclei remaining. Because both the activity and the number of radioactive nuclei remaining follow an equation that says A for activity is equal to activity you started with, E to the minus lambda T. And I assume you all remember, some people have just in the last 2 days updated their lab report or submitted their lab report from that lab. That's the equation for the activity or the rate. It was due earlier, Jordan. Don't look like you're missing something. Or we could be looking at the number of radioactive nuclei remaining, where lambda, the decay constant, is the value, the variable that tells you how likely it is each second for a particle to decay. And when I lectured on this during the lab period, I went through the derivation really quickly of where these equations come from. Well, that's the key for radiometric dating. What it says is, if I know how much I started with, either the activity or the number of radioactive nuclei, and I measure how many I have now, then I can just take how those numbers have changed and calculate the time, right? If I take, let's just take this one. Dividing both sides by A0, C to the minus lambda T. Well, if I take the natural log of both sides, natural log being the inverse function of exponential, I'm going to get natural log of A over A0 is equal to E to the minus lambda, or not E, got rid of the E, minus lambda T. Therefore, the time is equal to minus natural log A over A0 over that decay constant. So if I can determine what the activity is now and what it was initially, I can determine the age. What is this relying on for its fundamental working? What's our physics concept here? Okay, we have a certain decay constant that has to remain constant. It can't be just a decay constant that changes with time. It has to be a decay constant. So a fundamental assumption is that this is always constant. So how many people can go back and verify that that number hasn't changed from the last million years? We can't, right? We have to take some faith here. And there are plenty of people who say, but I believe it has changed. Where does that decay constant come from? It comes from the stability of the nucleus. And if you have things like the speed of light changing with time, the speed of light relates to the force of an electric, the force between electric charges. And so if the speed of light changes with time, that decay constant will change with time. And so you can find articles where people look at the historical measurements of the speed of light. And they say the first one that had an uncertainty this big was, I think it was faster. And then over time, the numbers have gotten lower and lower and lower. They find a trend in those numbers. And they say, see, the speed of light has been changing with time, and thus the decay constant has been changing with time. But what they ignore is like the first measurement of the speed of light had an uncertainty that was huge. And as the uncertainty drops, the values stay within the uncertainty range, but come toward a specific value. So that argument is pretty weak, but it is an assumption. We cannot do experiments really that will test the assumption that this decay constant has always been the same. A second important assumption is that you know A0, or alternatively N0, the number of radioactive nuclides you started with. If you don't know what you started with, you have nothing useful, right? You have to know where you started. So, yeah, that question is just looking at this. A half-life is the time for 1/2 of your radioactive isotopes to decay. 2 half-lives, you have 1/2 times 1/2 of remaining. 3 half-lives, 1/2 times 1/2 times 1/2. You're going to leave right when we have a clicker question?
Oh.
I mean, it was no secret here. I just got into it. Approximately how many half-lives result in less than 0.1% of the original nuclei remaining? That is less than 1/1000. I just don't want him to lose points in case you're following along here. You can go now. You don't have to stay in pain. Okay, 2 more. All right, we've all answered. Now I am going to have you turn to your neighbors and 2710208 and discuss this one because we have a fair disagreement. And I'm pretty sure when you discuss with the neighbors, you'll be able to determine which one it is. You'll accept it, will you, Jordan? That's good, because you are the one that's being called on. Okay, let's go ahead and answer again. And this time around, I will actually give you permission to push the button for Gabriel because we understand he had a situation that could not be avoided. Okay. This time the answers were very different. Oh, there's a 0 on top. Okay. Yes, each one of you was unique, believe it or not. Yes. When you look at the screen, I let them put the answer in for you while you're playing. Okay, so Jordan, as you know, I'm calling on you. Let's hear an explanation.
I chose C because if you look at the pattern, it is 1/2 to some power for percent remaining in the half-life. You take 1/2 to the 10th power, you're going to get 0.09, which you round it up, you get 0.1%.
Okay, perfect. Those of you who've taken computer science classes, you certainly know that like 2 to the 8th is 256. And then you multiply that by 2, 512, multiply it by 2 again, and you're at 1024. That's the first one that's going to be just under 0.1%. So that was the correct answer, and I am very pleased that things moved to the answer with only 1 after you discussed. That means the discussion worked. The one person I'm guessing was Erin, right? No, because I heard her explaining. That's why I was. Oh, the first set was all off by 1 as well? Okay, so there were 7 that said 10? Okay. So, yeah, it's I can't read the number. Thanks. That also is better. Now, carbon-14 dating. How is it done? Right, this was what was done on that Shroud of Turin. You start by saying, okay, we have to know how much carbon-14 was in the atmosphere. Let's talk about carbon-14 to get started. In the atmosphere, what is 79% of the Earth's atmosphere? Nitrogen. So we have a lot of nitrogen. And that nitrogen is getting bombarded by solar radiation. And so I believe it gets hit by a neutron. I didn't look this up, so I could be wrong. I believe that produces nitrogen-15, which is unstable, which quickly decays into carbon-14 plus, and if it's going to do that, what's it going to give off? A proton. I think that's the reaction. I didn't look it up before class, so I should have. So that's what's creating the carbon-14 in the atmosphere. So we have this carbon-14 being created in the atmosphere. There's constantly carbon-14 being created. Carbon-14 is then being absorbed by plants. Those plants are eaten by animals. Some animals eat other animals. So in the end, everything that is eating is taking in this carbon-14 that's created in the atmosphere. And so the ratio of carbon-14 to carbon-12 in the atmosphere is reflected in all of us. So we all have some carbon-14 in us. We're all radioactive with it. But when you die, you stop eating. And because you stop eating, you're not replenishing that carbon-14. And so in your body, you have, of course, a majority carbon-12. And what they measure is they measure the ratio of carbon-14 to carbon-12 in your body. Actually, I think it's carbon-13, but I'm writing carbon-12 here. The 12 to 13 ratio is pretty fixed. So they measure that ratio. And then they measure the ratio in some dead object. And if the ratio is different, then they use the same work that we did before, that the time since it died is minus the natural log of, the ratio divided by the initial ratio over the decay constant, or substituting in the half-life, you have the half-life over natural log of 2 times the natural log of the ratio of R0 over R. So basically, they measure the ratio, compare it to what the ratio was in the atmosphere, and they get an age. Anybody see a flaw in the ointment? Flaw in the ointment. Mixing metaphors. You want to see a fly in the ointment? Or flaw in the method? There's a really obvious one.
We don't always know how much carbon-14 has been around.
Yeah. In fact, we know it's not constant. How do we know it's not constant? Let's just go to that. Here's a historical calibration curve going through time back about 1,100 years, measuring from things that we can determine their age from something other than carbon-14 dating, and using that to calculate what the ratio was back when it died. And you can see there's lots of variation there. The minima there, the Oort minimum, the Wolf minimum, Spohr minimum, the Maunder minimum, those are periods of time when the temperature on Earth was really cold, right? We're still recovering from this Maunder minimum when the Earth was very cold. You can see temperatures there. We are actually higher, according to this graph, in carbon-14 than we were back at the medieval max, which suggests then the temperature is probably warmer than it was the medieval max as well, but that's not the point of today. Looking at more recent data, I was born, just for the record, you can see just a couple years before I was born, the amount of carbon-14 in the atmosphere changed dramatically because there was an eruption of volcano. The volcanic eruption changed the ratio dramatically. So now we go back, the assumption that this here is constant is horribly flawed. Now, if you listen to creation versus evolution debates, creationists will say, carbon-14 dating is useless because you're assuming that ratio was constant. That is a straw man argument. It's not true that they assume R0 is constant. They don't assume it's constant. If they did, it would be very valid that it wouldn't make any sense. So what they assume is that it's well calibrated. That going through and calibrating, finding different artifacts, such as, okay, here is a tree. We count the tree rings. How often does a tree make a tree ring? Once a year. Why? Yeah, the rate of growth varies with the temperature and moisture. It is not unknown for a tree to create 2 rings in a year if you have significant variation in the weather. But as a general rule, it's about 1 ring per year, and so they use that and they can calibrate. And so here is a calibration curve. This is looking at things that can be dated by archaeologists based on historical records, and then looking at how much carbon-14 to carbon-12 ratio there is today, and calculating what the ratio must have been back when it died. And so we get a curve there that they fit to try to understand what it was. Now, this next one is about Ötzi, the Iceman. You guys heard about that? Okay, so in dating the Iceman, they have an uncertainty in the ratio of carbon-14 to carbon-12. So here's the measured value, and here's plus or minus 1 standard deviation. And so they say, okay, based on this amount of carbon-14 to carbon-12 ratio that is in Ötzi, we're going to calculate how old Ötzi was. So now if we have to look at the top one, here's the uncalibrated curve. That is the curve just assuming we've had a constant ratio. And that would say that Ötzi lived at somewhere around 2550 BC. But that's not the conclusion for the age of Ötzi, because the calibration has this jagged curve that's based on looking at tree rings. And the jagged curve intrudes into the region where there is a plus or minus 1 standard deviation on the mean, 3 different places. And so they get 3 different possible ages for Ötzi, not just 1, but 3. And so those ages are in this span from around 3100 BC to 3350 BC. And if you look here, we have the actual dates and the probabilities for each date over here. So we have a 44% chance that it's 3360 to 3330 BC, or a 29% chance 3210 to 3190 BC, or a 28% chance 3160 to 3130. Right? So the actual method is much more complicated than what you tend to think, because they want to make sure they get it right. They still have the underlying assumption that the decay rate has been constant. We do have evidence that the decay rate does change in some unique situations, like when you have certain molecules, they found a very slight change in decay rate. So it's not perfect. And I have to point out that things are getting really interesting in terms of dating things like dinosaurs. Because somewhere around a decade ago, a scientist found what looked like blood vessels with red blood cells in a dinosaur. And as we understand from tissue preservation, There should be no tissue preserved from something that's 65 million years old. And there was a lot of resistance to doing things like radiometric dating or that kind of stuff because they're like, what's the point? How long is radiometric dating useful for? Well, the half-life for carbon-14 is 5,730 years. And after about 10 half-lives, you really don't have a measurable amount of carbon-14 remaining, which is why I had the 0.1% on the previous slide. So carbon-14 dating is really only good to about 50,000 years. So why would you try to date something that's 65 million years old with something that can only get you out to 50,000? Using certain techniques, some people will claim they can get out to even 100,000 years of carbon-14 dating, but that still doesn't affect a dinosaur. Well, what they found is they find a little carbon-14 remaining in these dinosaurs, which really confuses the issue. So we have now the vast preponderance of evidence suggests that the dinosaurs are, somewhere in the ballpark of 65 million years old, right? Going back to the Cretaceous period. Cretaceous? The Cretaceous, the Triassic, and the Jurassic. Hopefully I got those in the right order. But then we have a small minority of data that says that's not possible. And so there's reason here to study because we have some conflict. The physics, we think, is pretty immutable, and yet the biology suggests that we might be wrong. Now to the Shroud of Turin. The Shroud of Turin was discovered. Now that was, I should have, I don't have the actual date that was discovered, just that it first surfaced in the 14th century. So somewhere in the 1300s. The shroud was found and people said, this is the shroud that Christ was buried in. And for very long times, it was very much protected. Nobody could do anything with it as far as scientific study because it's holy and you don't want to desecrate the holy thing. And then they finally, in 1988, got permission to do radiometric dating on it. And so they snipped out a little piece over on the margin that they figured was not important to the shroud, and they tested it. And they found that little piece to be around 728 years old. Well, a little math means that it was, with their radiometric dating, basically that little piece dated to 100 years before it was discovered, suggesting that it wasn't the shroud that Jesus was buried in. But that doesn't end the controversy. As a believer, I know that it would take some pretty incredible evidence for me to give up my belief in Christ. Well, the people who believe this was the shroud that Christ was wrapped in have the same view. It's going to take some pretty incredible evidence. And they said, you took it from this little scrap, I don't know where it was, but that little scrap actually looks like it has been mended. And so quite possibly you just dated the material where they mended it when they found it, and it's not the actual date of the Shroud of Turin. It's a reasonable doubt. Of course, the problem is the same people who are saying that's not a reasonable piece to be dating are the same people who are saying, and you can't date the stuff that, is important. But, it's very interesting to me. While I'm on this, in my morning devotionals, I've been reading about all kinds of interesting things. And one of the things I read about, it's the Easter season. I was reading about the burial of Jesus. And I always kind of laugh at people who go to the Holy Land and pay money to see the tomb Jesus was buried in. Now, this is going off topic, I know, but I think it's interesting. How many tombs does Wikipedia list for Jesus being buried in? That is ones that people claim. You don't have to look it up. Just guess. It's actually only 5. 3 of them in Jerusalem. Makes sense, right? Because where did he die? Jerusalem. one of them in Kashmir, one of them in Japan. Now, I'm doing my little devotional, I read that, and I'm like, well, I've got to study this a little bit. The one in Kashmir and the one in Japan both have the common theme, that Jesus didn't die on the cross. The one in Kashmir says that, I think it was supposed to be, Arabs rescued Jesus and took him up, and he lived in this valley where he died. The one in Japan is more interesting. In 1933, this Hebrew writing was discovered that was the history of Jesus. And it said that when Jesus was around 20-ish, he came to Japan. And he sought wisdom there about, spirituality and whatnot for 12 years. And then he returned to Judea for his ministry. And then when things were getting a little dicey and he was arrested, his brother slipped in and took his place. His brother was crucified. He went back to Japan, got married, became a rice farmer, and had 3 daughters. And died at the age of, 109 or something like that. Now, I bring these up in class. They don't have anything to do with this. I'm sorry. But those 2 stories, the one about Kashmir and the one about Japan, those say Jesus didn't die on the cross. If he didn't die on the cross, what does that say about our religion? It's a waste of our time, right? If I were to believe those as true, which I think is pretty reasonable to not believe them true, then that would be denying that Christ died for our sins. And there's really nothing more important to me than Christ dying for my sin. Creation is pretty close. And so I just found that really interesting how to share it. Sorry for going off topic. Moving on. Nuclear energy. Actually, we've already talked about nuclear energy for the most part. We've talked about the nuclear power plants and nuclear bombs. Last thing here, the Earth's energy budget is 100% nuclear. 99% comes from the sun. How is the sun producing energy? Nuclear fusion. It's fusing hydrogen into helium in its core. So we have hydrogen atoms. How do you make hydrogen atoms fuse? What's the first thing that's difficult about making fusion occur? The what? Okay, you have to have high temperatures because hydrogen, in the sun, it's very high temperature. Collisions are so energetic that everything's completely ionized. There are no electrons bound to any nuclei in the sun. So you just have naked protons. Proton has a positive charge, another proton has a positive charge. They come toward each other, they repel. So you have to have them going really fast to actually collide. How do we measure their speed? With temperature. Because temperature is a measurement that tells us about the root mean squared speed. So the temperature has to be millions of kelvins. I believe it's somewhere around 15 million kelvins in the core of the sun. How do we know that? Well, clearly we put a thermometer in there, right? No, it's all based on calculations of how we understand physics. So it has to be very high temperature for them to collide. Furthermore, you want to have more than one collision every year. So if you're going to have lots of collisions, you also have to have a high pressure. So in order for fusion to occur, you have to have a high temperature and high pressure. In the sun, gravity provides that. Gravity is crushing everything, giving us the high temperature and pressure. Then we have the hydrogens that come together, they fuse together, release energy. That energy makes things hotter, makes things expand, and we have a balance, we call it hydrostatic balance, between the outward forces due to the energy released and the inward force of gravity. So the sun is a thermonuclear device. It's a fusion device. It's a huge, huge bomb. And that's why if you buy your Oakley sunglasses, they say on them, thermonuclear protection. Because they're protecting you from the radiation from the sun, the thermonuclear reactor. We would like to do something like that on Earth. Oh, crap. So on Earth, we want to try to replicate the conditions, but we want to be able to control it. we don't have the luxury of making something sun-sized, right? So we have to try to make small things where we can get the high temperatures and pressures necessary for fusion and yet not have it blow up. We can make high temperatures and pressures for fusion. All we have to do is make a fission bomb. You put hydrogen inside a fission bomb, you create the high enough temperature and pressure inside, and boom, you have a fusion bomb. That's actually how they make a fusion bomb. But it's not controlled. So there are two methods that are applied to try to control it. One is using inertial confinement, which basically they use laser beams to try to heat them up to high enough temperatures to make fusion occur. The other one is using magnetic bottles, what they call a tokamak. It's a Russian word. The other 99% of our budget comes from the sun. The other 1% is from radioactive decays inside the earth. We're out of time. I'll see you for your lab presentations tomorrow.